Hello viewers, I am Dr. Mala Das Sharma, retired professor of St. Pius X Degree and PG College for Women, Hyderabad. Let's start 50th episode of Teaching Chemistry through Riddle. So here is our riddle number 50, which goes like this. X is a type of reaction which can be classified into three categories. Out of three, one category is Y. Aliphatic halogen compounds are highly responsive to Y, whereas aromatic halogen compounds are repulsive towards Y. Depending on nature of the substrate, two mechanistic pathways of reaction Y are found in aliphatic halogen compounds. Same mechanistic paths cannot be followed by aryl halides. Instead, they follow other two pathways which look unrealistic and proceeds under drastic condition. So, this is riddle number 50. Now, let's see the question. The first primary question is, what are referred in the riddle as X and Y? Answer is X, substitution reaction, Y, nucleophilic substitution reaction. Second primary question is, what are the two mechanistic pathways followed by aliphatic halogen compounds during reaction Y? Answer is SN1, that is nucleophilic substitution unimolecular, and SN2, nucleophilic substitution bimolecular. The other questions are, third question, why aromatic halogen compounds are repulsive towards nucleophilic substitution reaction? Fourth question, why aryl halides cannot follow SN1 and SN2 reaction paths? Fifth question, discuss the mechanism of nucleophilic aromatic substitution reaction. So, let's see the third question. Answer, why aromatic halogen compounds are repulsive towards nucleophilic substitution reaction. So, let's start nucleophilic aromatic substitution reaction. We know that aromatic ring, so benzyne, delocalized pi electron cloud is present above and below the ring. So, this is the ring, so aromatic ring or benzene ring, and this p orbital of each carbon atom containing 1 electron, they overlap sidewise direction and form a pi-electron clouds, continuous pi-electron cloud above and below the ring, and this makes the ring electron rich. So, aromatic ring itself is electron rich and it undergoes electrophilic substitution reaction. It acts as nucleophile. So, nucleophilic substitution reaction in aromatic compounds, aryl halide, is unusual and occurs under special condition. Fourth question, why aryl halides cannot follow SN1 and SN2 reaction paths? See, in aryl halides, we don't find SN1 and SN2 reaction path. Why? We know that in SN2 reaction of aliphatic halogen compounds, the nucleophile has to attack from the back side of the leaving group. Now, this is the aromatic ring, and in the aromatic ring, if this nucleophile attack from the back side, it is in the one plane. If it attacks from the back side, then this will be the structure, which is the impossible structure. And for SN1 in aliphatic halogen compounds, what you have observed that the first step is the ionization. Here in aryl halides, if ionization occurs and the leaving group leaves, then this phenyl cation is formed. The phenyl cation is unstable. Why this phenyl cation is unstable? Because in aromatic ring, what we have observed that these p orbitals, they are perpendicular to the ring and they form the continuous pi electron cloud above and below the ring. But this positive charge is present in the sp2 hybrid orbital, which is at the plane of the ring. So, and these p orbitals are full. So, this positive charge or this positive charge in the sp2 hybrid orbital, this sp2 hybrid orbital cannot take part in resonance with this p orbital. So it is not stabilized by resonance. The only exception to this is when we have the excellent leaving group of gaseous nitrogen, and these are found in the reaction of aryl diazonium salt. This one, this diazonium cation, it leaves as nitrogen gas, and this is the example where we find that this is the excellent leaving group. Now, fifth question. Discuss the mechanism of nucleophilic aromatic substitution reaction. So, aromatic substitution reaction undergoes two mechanistic pathways. First one is addition-elimination mechanism. In this mechanism, the presence of an electron withdrawing group is mandatory. See here, this is chlorobenzene. When it is treated with sodium hydroxide in presence of heat, then no reaction. But when nitro group is present at the para position of the chlorine atom and it is treated with sodium hydroxide 100 degrees centigrade, then this substitution reaction occurs. So, presence of this electron withdrawing group is mandatory. Now, coming to the second mechanism, that is elimination addition mechanism, where benzyne intermediate is formed. Now, this benzyne mechanism works with a very strong base or strong nucleophile, and it does not require any electron withdrawing group. Say for example, see, this is chlorobenzene. Under drastic condition, when it is treated with sodium hydroxide at very high temperature, then this substitution reaction occurs. But if the nucleophile is strong, say sodamide, then at low temperature also this substitution reaction occurs. Now coming to the addition-elimination mechanism for this nucleophilic aromatic substitution reaction. See, here the first step or this rate determining step is the addition of this nucleophile. So this nucleophile, here it is OH minus, it attacks from either side of the face. This ring is in one plane, so it attacks from either, it attacks perpendicularly from either face, either top face or back face, down face. Okay, and then this carbanion is formed, which is resonance stabilized, and this is known as the Meisenheimer complex. So this addition occurs from either face, almost perpendicular of the aromatic ring, and the resonance stabilized carbanion, which is known as Meisenheimer complex, is formed. Now, next step, which is the first step, that is the elimination of the leaving group. So here the leaving group is eliminated and this product is formed and aromaticity is restored. Okay. Now here one question may come that when the leaving group is eliminated, there may be a possibility that instead of this leaving group, here it is fluorine, the OH minus also can be eliminated. So the nucleophile must be stronger base than the leaving group in order to favor the desired substitution product. The electron withdrawing group must be present in the ortho and para position of the leaving group. Right? Say, here the strong electron withdrawing nitro group is present para position of the fluorine. Fluorine is the leaving group. Okay. In the Meisenheimer complex, this resonance stabilized carbanion is formed. In presence of the nitro group in the para position, this resonance is extended up to nitro group, or what we can say, this nitro group stabilize this complex or stabilize this carbanion through this resonance effect or mesomeric effect. So we are getting one extra resonating structure when nitro group is present in the para position. Now similar things happens with the nitro compounds. See here also in the Meisenheimer complex, this carbanion is stabilized by resonance. We will get this 3 resonating structure. But in presence of the nitro group in the ortho position, this resonance is extended up to nitro group. So this carbanion is more resonance stabilized, or in other words, nitro group can stabilize this carbanion through resonance, more stabilize this carbanion. We are getting one additional structure. So when this electron withdrawing group present in the ortho position, then also the rate of the reaction will be faster and reaction occurs easily. But when it is in the meta position, then this nitro group cannot participate in resonance with this negative charge. So resonance stabilization is not possible, or nitro group cannot stabilize the carbanion by resonance. Only some stabilization occurs due to minus I effect of the nitro group, delocalization of the charge. But resonance stabilization does not occur. So when the electron withdrawing group is present in the meta position, the complex is not stable. Now, fluoride is the best leaving group among the halides in this SNAR reaction. See why. But we have observed that both SN1 and SN2 reaction, that is aliphatic halogen compounds, this carbon-hydrogen bond breaking is the rate determining step. In SN1 reaction, first step is the breaking of this carbon and halogen bonds and the carbocation is formed. And in SN2 reaction also, this nucleophile attack in the back side, from the back side and leaving groups left. That means in one step it happens. But in both the cases, this breaking of this carbon halogen bond is present in the rate determining step. Okay. Since the carbon fluorine bond is stronger than any other carbon halogen bond, so fluoride is the worst leaving group for the SN1 and SN2 reaction, because carbon fluorine bond is strong and this fluoride is the strong base. Addition elimination mechanism, rate determining step is the nucleophilic addition to the aromatic ring. And look at here, when this nucleophile is at here, as I told you, from either face it can attach, then this Meisenheimer complex or resonance stabilized carbanion is formed. No doubt this resonance stabilized carbanion, but here aromaticity is destroyed. So this one is less stable compared to this compound. That is, aromaticity is there, but here aromaticity is destroyed. So this step should be the lowest step or rate determining step, because when aromaticity is destroyed, this complex is not energetically very favorable. Okay? So this addition step is the rate determining step. Now, the formation of this Meisenheimer complex is the rate determining step we have seen, and the rate equation will be rate is equal to rate constant, aryl halide concentration and the concentration of the nucleophile, because in this step nucleophile is attached or added here. Now, what you have observed, the electronegativity of the halogen increases the rate of the reaction. So this is the decreasing the rate of nucleophilic substitution reaction. This is the order. That means as we are going from fluorine, this is the leaving group, fluorine to iodine, then the rate of the nucleophilic substitution reaction in aryl halide decreases. Then the question comes, why electronegativity of halogen increases the reaction rate? Because in the rate law we have seen that it's aryl halide and this nucleophile both are there, but this breaking of this carbon halogen bond is not in the rate determining step. Then what is the reason? See here, if it is fluorine, then this fluorine is highly electronegative. It attracts this carbon halogen bonded electron pair strongly through its minus I effect. So when it is attracting strongly, then this carbon atom becomes more electropositive. That means positive charge on this carbon atom will be maximum in presence of fluorine. Then when it is more electron deficient, then the nucleophile can easily attack this carbon atom. So in that case, rate of the reaction increases. And order will be fluorine to chlorine, then bromine. When iodine is there, iodine is the least electronegative. In that case, this electron deficiency on this carbon atom will be least. So, this nucleophile cannot attack so easily, so rate will decrease. So therefore, we have to consider how halogen affect the rate of nucleophilic addition in the first step and not just the loss of the leaving group. And we have seen that fluorine has the advantage, it is most electronegative. It activates the ring a lot more than the other halogen by decreasing the electron density so that nucleophile can easily attack, and through its strong minus I effect, it stabilizes this negative charge. Okay, when this negative charge is formed, through its strong minus I effect, it delocalizes the negative charge or stabilizes this negative charge. So again, this is the rate determining step, and it turns out to compensate and overcome the barrier of breaking of CF bonds. Benzyne mechanism in nucleophilic aromatic substitution. So it is nucleophilic aromatic substitution elimination addition mechanism. So this is elimination addition mechanism, and this reaction is OH minus. It requires the Brastic condition, but with the strong nucleophile, it works at low temperature if the base of nucleophile is very strong, and the reaction proceeds to the formation of a triple bonded benzyne intermediate. See here, this is chlorobenzene. Sodium hydroxide, it requires a drastic condition at 350 degrees centigrade, then this substitution occurs. But with sodamide, which is a strong base, then the reaction occurs at low temperature. Now we see the mechanism of this reaction, that is the elimination addition reaction. So in the first step, this nucleophile can take this proton from this beta carbon atom. Beta carbon atom in the sense this is the leaving group, and with respect to leaving group, this position is ortho position and this is the beta position. So it takes the proton from this beta carbon atom. Okay, so deprotonation occurs and this carbanion is formed, and then what happens? This carbanion, this electron pair, it forms a bond between these two carbon atoms, and this leaving group is left. So this benzyne, as this negative charge from this another bond, so triple bond is formed between these two carbon atoms, and this is called benzyne intermediate. So these two steps is the elimination steps. Okay. Now this benzyne, obviously it is very unstable. Then the nucleophile can attack either this carbon atom, because these two carbon atoms are triple bonded, either this carbon atom or this carbon atom. Okay, when the nucleophile attack this carbon atom, electron pair shifted to this carbon atom, you will get this carbanion, and then this carbanion takes proton easily, and then we will get the desired product. If the nucleophile attack this carbon atom, then also same product will be obtained, because we know that in benzene ring all the positions are equivalent. Now, why the deprotonation occurs at beta or ortho position with respect to the halogen? This is the question. See here, this leaving group or this halogen, it attracts this electron pair, this carbon halogen electron pair, by strong minus I effect. Okay, and then this minus I effect transmitted through the chain. So this carbon atom also acquires the positive charge, more positive charge compared to others. Okay, because this inductive effect is transmitted through the chain, and maximum will be in the second carbon atom after the first atom. So this carbon atom will be more electron deficient or will be more positive, and this is the beta carbon atom. So this hydrogen from the beta carbon atom or ortho carbon atom is taken by this, or this proton is taken up by this nucleophile, and this carbanion is formed. So this is a two-step beta elimination. Beta is the ortho position of the aromatic compounds, and this proton is most acidic. neutral and it is eliminated by the base in the first step. The negative charge is then stabilized by the inductive effect of the halogen because it is close to this halogen. No, it has strong minus I effect. So this negative charge getting more delocalized due to the strong minus I effect of this halogen and it is stabilized. Now here, according to March advanced chemistry, the leaving group is bromine or iodine. Proton removal is the rate determining. When chlorine and fluorine is the leaving group, breaking of CX bond or the formation of the benzyne intermediate is the rate determining step. See, here in Benzyne mechanism, this elimination is the rate determining step. But the elimination is taking place in two steps. Say here, if this leaving group or this halogen is fluorine, then what happened? Fluorine is strong electronegative. It has strong minus I effect. So this beta position or ortho position also electron density will be strongly withdrawn. So it will be more positive, more electron deficient. So this nucleophile can easily take the proton. And after taking the proton, as it has strong minus I effect, this carbon ion is getting more stabilized. So it is the most stable one. Therefore, this step will be the first step. It cannot be the slowest step. Then slowest step will be this one, where this strong carbon fluorine or carbon chlorine bond breaks and the benzyne intermediate is formed. So in presence of the fluorine and chlorine, this step cannot be the slowest step. This step will be the slowest step. But if it is X is bromine or iodine, where the electronegativity is less, inductive effect is less, minus I effect. So this ortho carbon atom or beta carbon atom is not very much electron deficient. Then this nucleophile cannot take this proton easily. That means deprotonation is not so easy. Then this step will be the slowest step or rate determining step. But regardless of the halogen, deprotonation of the aromatic ring and the resulting carbon ion is stabilized by the minus I effect of the halogen rather than resonance stabilization. Already I told you, after deprotonation, this carbon ion is stabilized by the minus I effect. This negative charge is delocalized, not localized in a particular position due to strong minus I effect of the halogen. Now, how triple bond is formed in benzyne? See here, suppose this carbon atom and this carbon atom, between these two carbon atoms, this triple bond is formed. Already we know that these two carbon atoms form this sigma bond by sp2 overlapping. And this p orbital, that is the pz orbital, which is perpendicular to the ring, they overlap sidewise and form the delocalized pi electron cloud above and below the ring. So, one pi bond is formed by this p orbital. Now, this carbon atom has this sp2 hybrid orbital where this negative charge is present, and this carbon atom has this sp2 hybrid orbital which is vacant now because the leaving group has left. They overlap and form the second pi bond. That's why this triple bond is formed. This is sigma bond and one pi bond through this p orbital and another pi bond through this overlapping of this sp2 hybrid orbital of carbon. So, one of the sp2 hybrid orbital of each carbon makes the single bond. One of the pi bond is formed by the overlap of the p orbitals just as it usually. And third one, and the second pi bond is formed by the overlap of two sp2 hybrid orbitals. Evidence for the formation of benzyne intermediate. See, one method for proving the formation of benzyne intermediate is using C14 isotope. See here, this is chlorobenzene. This carbon atom is replaced by isotope of carbon, C14 carbon, and this reaction, substitution reaction is carried out. In that case, this nucleophile will substitute this chlorine atom. That means amino group can be attached here to this carbon atom, and it is found that another product is formed where amino group is present or attached to this carbon atom, that is C12 carbon atom, not this C14 isotope. That indicates that Benzyne mechanism is formed. That means between this and this carbon atom, triple bond was there, and nucleophile can attack either this carbon or this carbon. So, each two group, amino group, would not end up being on both carbons if there was no Benzyne forming. Then, the reaction of parachlorotoluene with sodamide that produces a mixture of two constitutional isomers. So this is parachlorotoluene. When it is treated with sodamide, then these substituents, that is amino group, it enters here, that is in the position of the leaving group, and also another product, another isomer is obtained where it is in the ortho position with respect to this leaving group. Then we are getting the two isomers. One is with respect to this methyl group, it is the para position, so paramethyl aniline, and with respect to the methyl group, it is in meta position, so it is metamethyl aniline. So this observation can be explained by the nucleophilic attack of the amino group at both the carbons, that means here and here where Benzyne is formed. Both the carbon of the triple bond of the Benzyne intermediate. Now let's see. So first nucleophile will take this proton, that is deprotonation. Then this carbon ion is formed, here negative charge, and then this Benzyne intermediate is formed. Now in the Benzyne intermediate, when the nucleophile attack this carbon atom, then we will get this product, and when the nucleophile attack this second carbon atom, we will get two products. In the first case we got para-aminotoluene, and second case we got first case we got meta-aminotoluene, and the second case we got para-aminotoluene. So this is the discussion on this nucleophilic substitution reaction of aromatic halogen compounds. We have come to the end of this video. Thank you.